Hello friends, welcome to my channel Lahari Lectures. In this video, you can watch notes on paging in operating systems. In MVT, if there are two non-adjacent holes whose sum of their sizes is greater than or equal to program size, then two non-adjacent holes are combined into single hole by using compaction technique. However, this time-consuming process to overcome this paging is used. In paging, memory is allocated for the program at non-contiguous memory locations without actual combining them. That is, without combining the non-adjacent holes, program is stored non-contiguous and the details of this allocation is stored in page table. In paging, user develops a program having contiguous memory locations in his mind. However, memory may be allocated for the program non-contiguously. The view of the memory the user has is termed as logical memory, and the actual memory in the system is called physical memory. For a program to run successfully, mapping should exist between logical memory and physical memory. A user program in logical memory is divided into pages, each of equal length, and the physical memory is divided into frames. The page length and frame length must be compatible. Memory allocation for a job is done through frames. At only point of time, a frame may be free or occupied. The memory manager part of OS monitors the total free frames available, and one page needs one frame. Whenever a program is to be executed, the memory manager checks whether the total number of free frames greater than the number of pages of the program. If so, the program is transferred into physical memory at free frames. The frames need not be contiguous. Once the program is stored in physical memory, the details of the allocation is stored in a table called page table. Page table is stored in physical memory of the computer. Example, consider a logical memory of size 8K and physical memory of size 10K. Let us assume the page length is 1K. Let there be a program which takes 4 pages. Here we can see the logical memory, disk, physical memory, core, page table. So this is the diagram. The page table gives information regarding which page is present in which frame. Whenever an address is generated by CPU logical address during program execution, the memory manager checks in which page this address falls and find displacement. Displacement equal to logical address minus starting address of the page where the address falls. Now, the memory manager checks in which frame the page is falling and finds the physical address. Physical address equal to displacement plus starting address of frames where the page falls. Let the logical address be 1028 falls in page 1 and starting address of page 1 equal to 1k. Displacement equal to 1028 minus 1k, 1028 minus 1024 equal to 4. From page table, we observe that pages 1 falls in frames 8 and a starting address of frames equal to 8k. Physical address equal to 4 plus 8k. 4 equal to 4 plus 8 into 1024 equal to 8196. Example, let CPU generates address 4100. This address does not fall in any page. This called an illegal address. 4k equal to 40% equal to the 4095. This method has two memory accesses, one to the page table to retrieve the frame number and the second to the physical address memory location to retrieve instruction or data. This reduces the operating speed as memory accesses are doubled. If we can store the page table in associative memory, then time taken to retrieve the information from page table is negligible and the operating speed increases. In paging, there is an internal fragmentation. Let there be a job of length 5.5k, then this program requires 6 pages, IP equal to 1k, and in the 6th page 0.5 is wasted, which is internal fragmentation. Thanks for watching. Please like, share and subscribe my channel. Thank you.